1.5 matrix inverse. Division is not defined for matrices. It's kind of weird, but there's no such thing as division. We use a matrix inverse to solve this problem of not being able to divide. So if you think about a common algebra equation, how could you solve 4x plus 12 without dividing? If I wasn't allowed to say divide both sides by 4, I could still get around this by multiplication. I could multiply both sides by the multiplicative inverse of 4, which is like saying I could multiply by 1/4. And that doesn't seem all that complicated, right? That's going to solve the equation. That's going to isolate the variable and get x equals 3, just the same as if I was to divide both sides by 4, right? It's the same thing, but just for whatever reason, we don't have division when we're talking about matrices. A matrix has a multiplicative inverse if and only if the matrix is square, meaning 2 by 2 or 3 by 3 or 4 by 4, and its determinant is non-zero. So sometimes there won't be a multiplicative inverse. Sometimes an inverse does not exist. So one way to tell if it exists or not is to find this determinant. If the determinant is 0, there's no inverse. If the determinant is anything else, then there is an inverse. It exists. So find the determinant and tell if a multiplicative inverse exists. So I'm going to show you how to do this by hand, and then I'm going to show you how to do it by calculator. Of course, you're going to rather do it by calculator, but I got to show you how to do it by hand. It's kind of a weird process, but we basically have to take the diagonal product of going left to right minus the diagonal product going the opposite direction, okay? So essentially, the determinant of A is going to equal 2 times 2 minus -4 times 1. And a 2 by 2 is fairly simple. A 3 by 3 or anything bigger is going to be a lot harder. But this says 4 minus -4, or plus 8. The determinant of the matrix is 8. And that number is just, it's hard to even tell what even that means, but it's one number that describes the matrix, but more importantly, it tells me that an inverse exists. We can say A inverse exists. Now, the second example is a lot more complicated because there's more than just one diagonal. If you just do an X like I just did, you're going to miss some numbers. You got to get all of the numbers. And so we kind of do a little trick here. I've got 1, 2, 3 columns. I'm going to rewrite columns 1 and 2. So I'm going to make like a column 4, and it's going to be the same thing as column 1. And I'm going to do another column, and it's going to be the same thing as column 2. Now try really hard. I'm not very good at this, but try really hard to keep all of your numbers perfectly spaced and lined. I don't want to copy the whole thing. I'm going to end up with 5 columns total, not 6. Now, what I want to do is kind of similar to the one I just did. I'm going to take this diagonal product, 1 times -2 times 0. So I multiply those 3 numbers. I'm going to get 0, by the way. But I also have to do the same thing for this diagonal product and this diagonal product. Okay, there are 3 of them now, and then I run out of room. But 1 times -2 times 0 is 0, plus 0 times -1, this one. 0 times -1 times 3 is also 0. And 1 times 2 times 0 is also 0. Now, obviously, that's going to be 0. Now, remember, up above, it says if the determinant is 0, then there won't be an inverse, all right? But that's not the determinant. Now I have to subtract the reversed diagonals. And so I'm going to have this one. 1 times negative 2 times 3 is negative 6. And then I'm going to have this one. 1 times negative 1 times 0 is 0. And then I'm going to have this one. 0 times 2 times whatever. It doesn't matter. That's going to be 0. So if we clean that up, we've got 0 minus negative 6 is 6. That's your determinant. Okay. Since that is a square matrix with a non-zero determinant, we know that the inverse exists. Now that's not bad to do by hand. It's not terrible, but we can do it with a calculator. So check it out. If I go to my math sites and I prefer finding the one that says Desmos matrix calculator, but any matrix calculator will do. I need a new matrix, and let's go ahead and do the 3x3 one. So that was 1. This was a 1. This was a 2. This was a negative 2. Negative 1. And this was a 3. Okay, so I've got that matrix. Notice down at the bottom, DET for determinant. I can hit that button for determinant and then type in A, and there it is right there. I didn't even have to hit enter, it calculated that's 6. The determinant is 6. All right, if I wanted to do it for the other one, let's make a new matrix. It's a 2x2. We've got a 2 and negative 4, 1 and 2. And I want to do a determinant of B this time, 8. That's exactly what I got. So this is a simple website to use. I like this one. Those of you with graphing calculators, enter that matrix and then go into the calc menu and find DET, the determinant. So that's one thing that we can do. Let's move on. How to verify two matrices are inverses of each other. Now this is kind of weird, but this is going to be good review of something that's going to be on the quiz. So you need to be able to multiply two matrices. This is going to be good for that. So we want to check to see if those two matrices A and B are inverses. Here's what you have to do in order to verify. Multiply A times B. If you don't get the identity, you can stop because they're definitely not inverses. What you want them to be is the identity. You want A times B to equal the identity. That's what you want. And then you have to multiply it backwards and see if B times A is also the identity. So you're going to have to do two matrix multiplications. So this is going to be a good review for the quiz coming up. So A times B equals . Now, do you remember how to multiply? You want to look at the sizes and first determine if it's even possible to multiply. Oops, that's a 2. So remember, those two are the same. If those two are the same, then we're good, and the result is going to be that size, 2 by 2. So draw a 2 by 2 skeleton. And fill in the blanks. Now remember how this works. You always do rows before rows. You're going to do a row times a column, right? Row times a column. But if you want to think about it, think about this. The top row times the left column is going to be the top left entry. Top times left equals top left. So remember how we do this. I call it zipping up the numbers. You take the first one times the first one, that's negative 5. And you take the second one times the second one, that's plus 6. And so that top left entry is a 1. And so now we want to do top times right. The top times the right, we've got 1 times 3 is 3. We've got 3 times negative 1 is minus 3. That's going to be top right is 0. Now let's do bottom left. Bottom times left. It's really easy for your eyes to go crossed, but bottom times left, that's going to be 2 times -5 is -10, and 5 times 2 is +10. That's 0. Now bottom right, 2 times 3 is 6. 5 times -1 is -5. That's 1. Now remember up above what we're looking for. We're looking for the identity, and you should remember the identity is 1s along the diagonal and 0s everywhere else. That's what we got. That's the identity. Specifically, that's I2, but that's good. That's what we wanted. Okay, but what everybody forgets is you now have to multiply it backwards. That what we just did is not technically enough. Now we have to multiply backwards. We have to do B times A. So we just flip-flop it. B is -5, 3, 2, -1. A is 1, 3, 2, 5. That's not necessarily going to be the same thing. It may be, but it may not be. But I know that's going to be a 2 by 2, so I can set up my skeleton again. And I'm going to do top left. That's going to be -5 plus 6 is 1. Okay, good shape. Top right. Top right. That's -15 plus 15 is 0. Okay, looking good. Bottom left. That's hard to read, isn't it? Bottom left. That's 2 and -2. 2 minus 2 is 0. And then bottom right, 2 times 3 is 6. -1 times 5, that's going to be 6 minus 5 is 1. So again, I get I2. That's exactly what I want. So step 3, if AB and BA are both equal, the identity, A and B are inverses. So verify that the matrices are inverses. They are. It's a tough question. Now you're looking at me like, well, why don't I just take one of the matrices and just plug it in and find its inverse? And okay, 1, 3, 2, 5. So check it out. If I'm on this side and I go, okay, new matrix, we're going to say that's a 1 and a 3 and a 2 and a 5. Enter. I want to take C inverse. Okay, notice I can find the inverse. It's easy to find the inverse. Notice that's not the same thing as to the -1st power, though. It's not the same thing. We're not doing it to the -1st power. That I don't know why they picked the exact same notation, but it's not the -1st power. That means inverse. But that result over there is the inverse, right? -5, 3, 2, -1. That's what we got. That's what we wanted. Those two things are inverses of each other. But when they say, if the question says verify, this is what they want. Now, main event, how to find a multiplicative inverse for a matrix by hand. This is assuming you aren't looking at a calculator and just punching it up and finding it in 2 seconds. If you had to do this by hand, this is what you would do. Step 1 says form an augmented matrix A bar I. So what I mean by that is you've got this matrix. I'm going to turn this into a bar, and I'm going to put I. In this case, it'll be I2 because that's the size that I would need. Whatever the size of your matrix is, that's the size of your I. So step 1 says form that augmented matrix. That's A bar I. Then it says perform row operations using Gauss-Jordan until you have I bar B. So essentially that just means do Gauss-Jordan. And so Gauss-Jordan, if you remember, this is another good review. Gauss-Jordan wants numbers here and zeros here. Specifically, it wants 1s along the diagonal and zeros there. But if you have 1s along the diagonal and zeros there, it's going to be the identity. So by doing Gauss-Jordan, we're producing the identity on the left side. That's what we want. So I'm going to use this 2 to zero out this 1 right there. We need a rule for that. We've done it for like a week, so it shouldn't be fairly new. You know, it shouldn't be new to you. I'm going to do 2 row 2's minus row 1. 2 row 2's minus row 1. So the top row's fine. Leave it alone. I'll move it right here. We good? Question? Over here? That's where we start because that's the identity. And that's, yes, that's where we start. So yes, absolutely. So the top row can stay the same, 2, -4, bar 1, 0. But that bottom row, I'm going to apply my rule because I want to knock this 1 out. I want this 1 to be a 0. So 2 of these minus this, that's 2 minus 2, that's 0. I just go all the way across. 2 of these is 4 minus this, so that's 4 minus -4. Be careful. That's 4 minus -4. That's going to be 4 plus 4. That's 8. 2 of these is 0. Minus 1 is -1. 2 of these is 2. Minus this 0 is 2. Now again, remember what we want. Gauss-Jordan wants numbers along that diagonal and zeros elsewhere. Now technically we want 1s along the diagonal, but we can do that at the end. I think that's the easiest way. Let's knock out this -4 using this 8. So I need another rule. It has to do with the LCM. So LCM's 8. I need 8 minus 8. I'm going to do 2 row 1s plus row 2. That would give me -8 plus 8. That'll be 0. That's exactly what I want. But I have to do it all the way across. So 2 of these row 1s, that's 4, plus this 0, that's 4. And 2 of the -4s is -8, plus this 8 is 0. And 2 of these 1s is 2, plus this -1, that's 2 plus -1 is 1. Feel free to use a calculator if you need. 2 of these zeros is 0, plus this 2 is 2. And then the bottom row, I didn't really need to do anything with anyway. 0, 8, -1, and 2. Okay. I'm in pretty good shape, except I want those to be 1s. In order to be reduced row echelon form, I want those to be 1s. So all I'm going to do, I've got my zeros, that's what I need. All I'm going to do is divide by 4 on the top and divide by 8 on the bottom. And this might confuse you because you're going to end up getting fractions over there on the right side, but that's going to happen. Sometimes you can't avoid fractions. By doing it this way, I've allowed you to avoid fractions for most of the way, but now we're going to have them. If you divide by 4 all the way across, you're going to have 1, 0, bar 1/4, 2/4. Second row, if you divide by 8 all the way across, you'll have 0 and 1, -1/8, and 2/8. And you should notice that you've got the identity on the left. That's what we're looking for. All right. So what we're trying to do until you have the identity and B, that matrix right over here, that's your inverse. That's what we're looking for. Of course, we would reduce the fractions. 2/4 is 1/2 and 2/8 is 1/4. But you've got your inverse is that matrix B right there. 1/4. 2/4 reduces to 1/2, -1/8, and 2/8 reduces to 1/4. Done. Now, of course, you could always check on a calculator. 2, -4, 1, 2. 2, -4, 1, 2. I want to do the inverse. Okay. Ooh, look over here on the right. There's a button that looks like it's going to change to fractions for me. Yeah, interesting. I can go back and forth by hitting that button. Fractions. 1/4, 1/2, -1/8, 1/4. Boom, got it. Okay, so that's pretty cool. I've got it. I can do it by hand using Gauss-Jordan. Obviously, you can do it by calculator. Got it. Now, number 3. Find the inverse, and it's a much bigger inverse. It's a 3 by 3. Okay, so the steps say to do this. Augment or add to it with the identity. And so if we were going to do this by Gauss-Jordan, we would have to turn this into the identity. We want numbers along that diagonal, specifically ones, and zeros here, 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 here. Okay? Well, let's just do it on the calculator instead. Okay? We've got this set up. Let's do an RREF. Let's do an RREF of that. So those of you with graphing calculators, you should know what to do from the other day. And the rest of us, we go into the math sites, and what are we doing? Gauss-Jordan elimination. We're going to do Gauss-Jordan elimination. So when you get to this site, remember what you have to do. You have to tell it the size. This size is a 3 by 6. That's a 3 by 6. And so now we need to enter in all those numbers and stuff. Okay. So I've got, might be easier if I type them. This one's a 1, 0, 1, 1, 2, -2, -1, 0, 1, 0, 3, 0, 0, 0, 0, 1. Let's see if this works. All right, sweet. That's our reduced row echelon form, I guess. Let's look at the fractions, and the bar's in kind of a weird space because it doesn't realize what we're doing, but this appears to be right. You've got a 1/3, you've got some 1/2. That's what it is. So trust me on this. I just saved you a lot of work by not making you do this by hand. But we did a reduced row echelon form, and we turned it into 1, 0, 0, bar, 0, 0, 1/3, 0, 1, 0, -1/2, -1/2, 1/2, 0, 0, 1, 1, 0, -1/3. Okay, if you noticed, what we've just done is we've changed it from AI to IB. And that B over there is the inverse. And so we're going to have an inverse that's equal to that B. Now, guys, I just saved you a lot of work. I gave you an enormous shortcut by allowing you to use that calculator and not having to do it by hand. All right? Don't try to shortcut it any more than this. Everything that's on the screen needs to be written down, including the fact that you used a reduced row echelon form. Whether you use your graphing calculators or that website doesn't really matter to me, but I need to know how you got there. All right. And I don't want you to skip all of the work and just write the answer. All right. Great that you can do it, but you do need to still show me how you got there. You still need to explain your answer. And so if you're not going to write anything else, you would at least need to, well, I don't want you to do that. So I'm not even going to say that. But this is what I want. But by the way, if it's a smaller one, be prepared to have to do this one by hand. Be prepared to have to do a small one by hand. Probably wouldn't make you do a big one by hand on a test or something like that. Now, the last part, it looks really, really complicated. And I know a lot of the times people don't read their math book or their math text, their math notes. Anytime there's symbols or language, you just kind of skip over it and look for numbers. But in order to be a good math student, you need to improve at being able to read your math, okay? So I want you, when we get to a gray box like this, I want you to try really hard to read it and not just skip over it. So this says, form how to solve a systems of equations using the matrix inverse. Form a matrix equation AX equals B, where A is the coefficient matrix, or just the numbers, X is a column vector of variables, and B is a column vector of constants. What I mean is this. If you look at number 4, and you took out the coefficients, notice this is a 1 right here, but if you made this into a matrix equation, it's going to look like 2, -3, 1, 5 for the coefficients. And then you're going to have a column vector, which is the vector of variables. Now, if you think about it, that's a multiplication problem. It's matrix times matrix, and we do row times column. If you multiplied the top row times the one and only column, you're going to have exactly 2x minus 3y. And if you multiply the bottom row times the column, you'd have exactly 1x plus 5y. So all I've done is turned that system into matrices, and that's going to equal the column of answers. That is a matrix equation, an equation using matrices, but it says the exact same thing as the system of equations that we're a lot more comfortable with. Step 2 says, and this is the biggie, we're going to multiply both sides by the inverse. So, recall earlier when I said, how could you solve the equation? How could you solve the equation without dividing? So remember when we multiplied by 1/4? That's what we're doing. Instead of dividing both sides by 4, we're multiplying by the multiplicative inverse. We're multiplying by the multiplicative inverse, and that's exactly the same concept that we're going to use here. Okay, so this equation, capital letters usually indicate that they're matrices. So think about that equation kind of like the 4x equals 12. If I wanted to solve that, I could multiply both sides of the equation by the multiplicative inverse. I can't divide by 4, but I can multiply by 1/4. I can't divide by capital A because I can't divide matrices, but I can multiply by the multiplicative inverse. And that's exactly what I'm going to do. In this equation, the 4's canceled out and leaving with just x equals whatever, right? That's exactly what's going to happen here. The inverse is the matrix that cancels out the matrix. A inverse cancels out A and leaves me with x by itself. X is going to equal whatever this is. This is a big deal. And this blows kids' minds, and they always this is a test question, and it should be easy, but people haven't thought about it enough to really understand what's happening. Okay, so if I'm going to solve this, This is A, and this is X. And A times X equals B. That's my matrix equation. So in order to solve this, I want to multiply by the inverse. That cancels this and leaves me X by itself. X is going to equal whatever the inverse of that matrix is times this matrix. Okay? Now I don't know, I don't know what the inverse is. I don't know what that inverse is, but it's going to be something times 4, 2. So there's a couple of different ways that you can handle this, but no matter what, you're going to need that inverse. In order to do it this way, you're going to need that inverse of 2, negative 3, 1, 5. 2, negative 3, 1, 5. Well, did we already do that? Let's see. I don't know. New matrix. 2, negative 3, 1, 5. And let's find E inverse. E. We get that nasty looking thing right there, okay? E inverse, change to fractions, looks like 5/13, 3/13, negative 1/13, and 2/13. Okay, fine. 5, 3, negative 1, 2. 5, 3, negative 1, 2. So it was 5/13, 3/13, negative 1/13, 2/13. X is going to equal, capital X means a matrix, the matrix of variables, X and Y, equals this multiplication problem. And so if you multiply matrices, again, this is a good review. This is a 2 by 2 times a, remember, rows before co's. This is a 2 by 1. If you take a 2 by 2 times a 2 by 1, you're going to get a what? 2 by 1. So skeleton, look like this, 2 by 1. This is kind of rough with the fractions. Maybe you need to make your bubbles bigger. But we want to do row times column right there. When I zip up the numbers, 5/13 times 4 is 20/13. And 3/13 times 2 is 6/13. That gives me 26/13, which is 2. Now I do the same thing for the bottom. Bottom times the column. Bottom times the column, I'm going to have negative 1/13 times 4 is negative 4/13. And 2/13 times 2 is 4/13. That's going to be 0/13, which is 0. Okay? So at the end of all that, I got my X matrix. My X matrix just tells me what X and Y are. This is X and this is Y. So X equals 2, Y equals 0. Or let's do a new matrix. And let's call it a, what was it, a 2 by 1? 2 by 1. Okay, the matrix of coefficients, or no, the matrix of constants was 4, 2. Right? 4, 2. Literally, all I have to do to find my answer is take the inverse of the first matrix times that matrix right there. That's it. 2, 0. 2, 0. Got it. X is 2, Y is 0. So people get really confused by all of this writing. Okay? All of this writing is really confusing, but essentially all I'm doing is I'm multiplying the inverse times that matrix. That's it. That's all I'm doing. Questions?